welcome again. So today's lesson will be on shipwrecks and salvage, and in particular we'll be looking at how do we actually use electrolysis for preservation of items that we take out of shipwrecks. Okay, so we've studied electrolysis and electrochemistry in great detail in how to preserve things from corroding, and in today's lesson we're actually going to see how we can use electrolysis to preserve artifacts that we've taken out of shipwrecks. Okay, so we'll just talk quickly about chlorides and artifacts. So as I mentioned in previous lessons, chlorides left in artifacts can be damaging because they form HCl. Okay, hydroxychlorides react with water to form HCl in general. Okay, so for instance, iron hydroxychloride, which is this one, can react with water to give you iron hydroxide and hydrochloric acid. Okay, so this is sort of that rust. It could be white actually as well, and this is obviously hydrochloric acid, which is damaging. If you have a copper compound, copper hydroxychloride plus water gives you the same reaction except with copper instead of iron. Okay, so we get HCl out, which is of course damaging to our artifact. So what happens in the actual electrolysis when we want to remove chlorides? Well, we have the artifact submerged in a dilute NaOH solution, okay? And it is the cathode of an electrolytic cell. So we want to try and reduce it, okay? So the reaction that's happening is that the iron hydroxychloride or copper hydroxychloride is gaining electrons, and you're getting back the iron solid plus OH minus and chloride ions. Okay? Now this reaction here, this top one, actually is what's happening, but we can actually simplify it because the only thing that's actually interacting with the electricity is the ion, and so this is more of a simplified reaction. Okay? Now at the anode, you get 4 OH minus turns into oxygen gas, water, and 4 electrons. As well, you get 2 chloride ions turning into chlorine gas plus 2 electrons. Okay, so from this animation here, you can see that once the OH minus and chloride ions have been liberated from this material, they actually, because they're negatively charged, drift over to the anode. And then these two reactions happen to remove them from the system. Okay, so you remove them as hydrogen gas and chlorine gas. So the anode, as I mentioned, will attract the negative ions and will oxidize them to produce water, oxygen, and chlorine gas. Okay? Now with cleaning, we can actually use electrolysis to clean your artifacts. So electrolysis can be used to clean as well as preserve. After chlorides have been removed, electrolysis can be used again to clean the object. So we use it once to get rid of chlorides, and then we can use it again to clean the object. And we use different processes, obviously, for different metals because each metal has a very different demands. So we need to just be careful of which process we actually use. So for iron and steel, after we've leached out the chlorine, we'll have mostly metallic iron as well as Fe2O3, so iron oxide. So that's what we have left over. Now what we can do is we can actually heat this piece of metal in a reducing H2 environment, which actually removes the Fe2 and gives you back metallic iron. Here's our reaction. So if we have hydrogen gas, the Fe2O3 reacts with the hydrogen gas to give you FeS, Fe solid, the metal, and water, okay, which is great. So we're back to basically iron and water, which is back to what we actually started with originally. The cleaned object can then be coated in polyurethane, which is just like a polymer plastic, to protect it. Now we have silver and copper artifacts. Now they are different, obviously, to iron artifacts. And so copper and silver form sulfide compounds as opposed to oxide compounds because of these sulfate-reducing bacteria. And under aerobic conditions, silver bromide and silver chloride are important corrosion products. Okay? So when we bring them back to an aerobic environment like terrestrial land, silver bromide and silver chloride become important. So following the removal of the concretions, so any like bulges of bacteria and things like that, by soaking in acid, we actually just soak in acid to remove all those concretions. Corroded silver artifacts are cleaned in a sodium hydroxide solution using electrolytic reduction cleaning. So we just use electrolysis again. The artifact forms the cathode, and a platinum titanium anode is used. So the silver sulfide is reduced to form silver metal and sulfide ions. And the sulfide ions react with the water to form hydrosulfide ions and hydroxide ions. Okay? So water is also reduced at the cathode, and the evolved hydrogen helps to lift layers of corrosion. So it actually helps to like pull off corrosion layers by bubbling underneath it. Okay? So that concludes today's lesson on electrolysis and how we use it in the preservation process. So we looked at using electrolysis for leaching and preserving, and we used it also for cleaning. Okay? So we'll move on to the question segment and see if we can answer some questions. So which statement concerning artifacts is correct? Artifacts are sheets of paper describing important artworks. That's not one. Doesn't relate to chemistry. Artifacts are any object recovered from past human society. That could be true. Only objects from shipwrecks are considered artifacts. No, because anything on land we can consider an artifact if it's been around for long enough. And artifacts are objects that have been buried. Obviously not if we have artifacts in the ocean as well. So B is the answer. Artifacts are any object recovered from a past human society. Okay? So any society, anything that they have that we've collected again, we call that an artifact. How do submerged objects become saturated with chlorides and sulfates? Well, the seawater dissolves the salts in the object. Nope. Chlorides and sulfates diffuse faster than the other salts in the ocean. Could be. Seawater diffuses into the objects and saturates. That's more likely than this one. And all of the above, well, probably not D. The answer is C. So the seawater actually just diffuses into the object and saturates it. That's all. What are concretions? Well, basically, it's pretty obvious that it's hard layers of calcium carbonate, sand, and corrosion, and marine life encrusting artifacts. So they're basically just lumps of sand, calcium carbonate, corrosion products, and bacteria that are just stuck onto artifacts. Okay? So outline the method used to monitor the progress of salt removal in the desalination process. Okay? So when we actually want to remove those chloride ions from our artifact, how can we monitor how much chloride has actually come out of it? So we monitor the chloride ion concentration in the wash water. Okay? So the water that the artifact is sitting in will start to get chloride ions in it, and so we can look at that to actually see how much has come out. This can be done by precipitation with silver nitrate or by using a chloride-specific electronic probe. So you could use a probe and a data logger, or you could precipitate it and weigh it and then do like a gravimetric analysis. So it's up to you on how you manage that. As ions are removed from the object, the chloride ion concentration in successive washes drops. So as you wash your artifact, you should see that there's less chloride ions each time you wash it, because they're not in your artifact anymore. Describe and draw a labeled diagram of an electrolytic cell suitable for removing deeply embedded salts from metal artifacts. Okay? So first thing, we get some kind of container, some kind of inert anode, and the object that we actually want to remove the salts from. We fill it up with NaOH electrolyte, dilute, remember, and then attach a power supply where the negative terminal is attached to our object and the positive terminal is attached to our electrode. Okay? And that's how we would remove salts from a metal artifact. And you can see the electrons are flowing in this direction. Okay? Construct equations to show anode and cathode reactions in an electrolytic cell for removing salts from artifacts. Well, at the anode, you could have this, the OH minus that comes out of the artifact, turns into water and oxygen. And the Fe, the iron hydroxychloride, plus 2 electrons gives you iron solid plus OH minus plus chloride ions. Okay. So that concludes today's lesson on using electrolysis for preservation and restoration. So we looked at how we can preserve artifacts using electrolysis and how we can actually clean artifacts with electrolysis. So hopefully your knowledge of electrolysis has allowed you to understand these processes, and hopefully you've learned about new applications for electrolysis. So look forward to seeing you at our next lesson.